Hello everyone. So I hope you are all doing good. Today's our topic is electrostatic potential and capacitance NCERT section 2.14 to 2.15 example 2.9 to 2.10. Disclaimer: the images, text, and other materials used in our presentations are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathi@iitk.ac.in and we shall remove the content immediately. Please note that the parts of the content may have been generated using generative AI, which is experimental. So the topics that we are going to cover today is combination of capacitors, capacitor in series, capacitor in parallel, example 2.9, energy stored in the capacitor, and example 2.10. We can combine several capacitors of capacitance C1, C2 up to Cn. So what is combination of capacitor? So if we want to attain any required capacitance more than if we have capacitors of capacitance some C1 and C2 and we want some more capacitance than these two or less capacitance than these two, so or the capacitance that is not uh, equal to that two capacitors but in between that two capacitors, that's why we combine several capacitors of capacitance C1, C2 or up to Cn. So we just required combination to acquire the required capacitance uh, that we want in the circuit without that we want in the circuit to obtain a system with some effective capacitance C. Okay, effective capacitance depends on the way the individual capacitors are combined. Two simple possibilities are discussed here. One is capacitors in series and one is capacitors in parallel. So if we want to acquire some required capacitance in the circuit that we don't have any capacitor of that capacitance, suppose if I want 6 microfarad capacitance in the circuit but I have the capacitance two capacitors of 8 microfarad or 10 microfarad or have any capacitance of any two capacitors of different capacitance and I want to acquire 6 microfarad. So I just want to acquire this capacitance by using the combination of these capacitors. So the first topic is capacitors in series. So capacitors in series. So when one plate of one capacitor is connected to another plate of the capacitor, means one plate of capacitors in series. It is the picture showing the capacitors in series. Okay, so when we can say that capacitors are in series, when one plate of a capacitor is connected directly to the other plate of the capacitor without any internal joint. So the connection wire, this connection should not have any other connection with some other part of the circuit. Means that plate should directly be connected to this plate. Means that plate should directly be connected to this plate. There should not be any other connection between these plates. Means you can't have connection like this from middle of this connection. Then this will no more, these capacitors will not more in series. Okay, so what is series combination? When one plate of capacitor is directly connected to another without any internal connection. Okay, figure showing combination of two capacitors in series. For capacitors C1 and C2 connected in series, when a battery is connected across the combination, the left plate of C1 and right plate of C2 acquire charges Q and minus Q respectively. Okay, so for capacitors C1 and C2, when they both are connected in series, when battery is connected across it, if these two wires are connected across any battery, okay, this term this connection this part is connected to positive terminal of the battery, that's why here positive charges appear, and this part of the other capacitor is connected to negative terminal of the battery, that's why negative charges appear. Okay, so when a battery is connected across the combination, the left plate of C1, this one, and right plate of C2, this one, acquire charges plus Q and minus Q. So when we connect these two capacitors across the terminal of battery, this plate will acquire plus Q charge and this right plate of C2 will acquire negative charge. Right plate of C1 must have charges minus Q. So right plate of C1, this plate, must have charges minus Q then, and left plate of C2 must have plus Q to maintain zero net charge on each capacitor. So by the definition of capacitor, we know that the if there is a parallel plate capacitor or capacitor containing two conductors, if there is positive Q charge on one plate, then there should be negative Q charge on the other plate, so that net charge on the capacitor will be zero. So similar concept applies here. If the left plate of C1 is at positive Q due to connection with positive terminal of battery, and this right plate of C2 is connected with negative terminal of battery and it requires minus Q charge. So then this right plate of C1 should have minus Q charge and this left plate of C2 must have plus Q charge, so that the net charge on the capacitor will be zero. So to maintain net charge on each capacitor. Okay. So right plate of C1 must have charge minus Q and left plate of C2 must have charge Q to maintain net charge on each capacitor. If this was not the case, an electric field would exist in the conductor connecting C1 and C2. So this is the wire which is connecting these two capacitors. If the net charge on both the capacitor is not zero, if this was not the case, this second case will not be true, then what would happen? If this capacitor has not net charge zero and also this capacitor have some non-zero charge, so electric field would exist. Electric field would exist from negative charge, positive charge to negative charge. The capacitor on higher potential and capacitor on negative potential means which capacitor will have more net positive charge will at higher potential and which capacitor have more negative charge will have at lower potential. So electric field would exist from higher potential to lower potential connecting C1 and C2, causing charge flow until net charge becomes zero on both the capacitor. So electric field would exist if net charge on both the capacitors is not zero, and this electric field will remain as it is till the net charge on both the capacitor become zero. So this electric field will cause redistribution of charges. Till then, charges on both the capacitors, net charge on both the capacitor become zero, and the connecting conductor has no electric field. Okay. Therefore, in series combination, the magnitude of charge plus minus Q is same for both capacitor. So in series combination, the magnitude of this charge plus minus on both all the capacitor that are in series combination is same. So charge on all the capacitors in series combination is same. This is the important point. In series combination, magnitude of charge plus minus Q is same for both the capacitor or all the capacitors that are connected in series. Capacitors in series. The total potential difference V across the combination equals the sum of potential difference V1 and V2 across individual capacitor. As I have already mentioned, that total potential difference that is of battery or external source is divided into the two capacitor according to their capacitances. Okay, so total potential difference V across the combination this V is across the combination of both, but individual potential difference is V1 and V2. Potential difference will get distributed. Charge remains same in series, but potential difference will get distributed across the each capacitor according to their capacitance. Okay, so potential difference V1 and V2 across the individual capacitors. So V equal to V1 plus V2. So potential difference, net potential difference across the combination is V1, that is the potential difference across first capacitor, V2, that is the potential difference across second conductor. So we know that C is equal to Q by V. Okay, so what is V? Q by C. So what is V1? Potential difference across C1 capacitor is Q upon C1. Q is same for both the capacitors. So V1 is Q by C1 plus V2 equal to Q by C2. Okay, so from here you can see that V1 is inversely proportional to C1. So in series combination, the capacitor having higher capacitance will get lower voltage across it, and capacitor with lower capacitance will get higher voltage across it. Okay, so the capacitance with higher capacitance having lower potential difference across it. Okay, potential will distribute according to their capacitance, and it is inversely proportional to the capacitance in series combination. And if number of capacitors are connected in series, so the capacitor with higher capacitance will get the largest, the capacitor with highest capacitance will get lowest voltage across it. Okay, so from here V equal to Q by C1 plus Q by C2. So from taking Q common and after rearranging, Q will go there. So it will become V by Q equal to 1 by C1 plus 1 by C2. Okay, so what is V by Q? V is the potential difference across the combination. Q is the charge on each capacitor. Okay, charge in the series. So V by Q, what is C? C is equal to Q by V. So V by Q becomes 1 by C. And what is that C? C is the capacitance of the combination. Equivalent capacitance of the combination. So the effective capacitance or equivalent capacitance C of the combination is given by C equal to Q by V, we know. So V by Q becomes 1 by C. So comparing this with the previous equation, it will become 1 by C equal to 1 by C1 plus 1 by C2. Okay, so this is the equivalent capacitance in the series combination. Okay, so what you can infer from that result, that in series the effective capacitance of the combination is less than the least capacitor with capacitance exist. Means if there is a capacitor exist, if there are number of capacitors are there in series combination and the capacitor with least capacitance exist, so the equivalent capacitance will be less than that least capacitance. Equivalent capacitance will be less than the smallest capacitance in the series. Okay, the derivation can be extended to n capacitors in series if there are n capacitors in the series. So this is the diagram. If there are n capacitors C1, C2, C3 and C up to Cn are connected in series, so combination of n capacitors in series, for n capacitors V1 V equal to V1 plus V2 so on up to Vn. So potential difference will distribute across each capacitor, which is equal to Q by C1 plus Q by C2 plus so on up to Q by Cn. Following similar steps, the effective capacitance for n capacitors in series is 1 by C equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on up to 1 by Cn. Okay, so effective capacitance is 1 by C equal to 1 by number of capacitors that are in series. So 1 by C1, 1 by C2, or up to n number of capacitors. Okay, so this is the generalized result for n capacitors in the series. Okay. So capacitors in parallel. So this is the diagram for capacitors in parallel, A diagram. So this is, there are two capacitors that are connected in parallel. Okay, so what is parallel combination? When one plate of all the capacitors in parallel combination are connected at one common point, and another plate of all the capacitors in parallel is connected with one common point. So this is the common point. Suppose these are the common points. So this plate of both the capacitors is are connected to this common point, and this plate of both the capacitor is connected to this common point. Okay, these are combination of two parallel capacitors. Okay, so in diagram B there are n capacitors in the parallel. So this positive plate of all the capacitors are connected to this common point, and negative plate of all the capacitors is connected to this common point. Okay, so capacitors are said to be in parallel when one plate of all the capacitors is connected at one common point, and another plate of all the capacitors is connected at another common point. Parallel combination of A, two capacitors, and second diagram is for n capacitors. When two capacitors are arranged in parallel, they experience the same potential difference. Okay, so when they are connected in parallel, in series, there was same charge in the across all the capacitors. Now in parallel, there is same potential difference across all the capacitors because they are connected at one common point. Their plates are connected at one common point. So potential difference across this common point is V. So potential difference across all the capacitors is V. So when two capacitors are arranged in parallel, they experience the same potential difference across them, but different charge on them. Okay, now the scenario is reversed. In series combination, same charge across all capacitors, but different potential difference. Now same potential difference across all the capacitors, but different charges across all the capacitors. Now why we use the parallel combination? So if we have a battery of low voltage and we want high capacitance, so we have to store large number of charges. So we will arrange them in parallel so that if there is a battery of 12 volt. Okay, so if I connect capacitors in series, this 12 volt will distribute among 6 or 7 capacitors in the ratio in the form of that if all the capacitors are of same capacitance, so 2 volt will get to all capacitors. Okay, so 2 volt is very less amount for any capacitor to store charges. So we want that every capacitor will store charge at 12 volt. Okay, so we will connect it with the parallel combination. So all the capacitor will have potential difference across them 12 volt. Okay, so now they will store charges accordingly according to their capacitance, and this 12 volt battery will serve the potential difference to all the capacitors in the series. Okay, and high capacitance will be achieved at very low voltage. So in this condition, parallel combination is used. However, the plate charge is plus minus Q1 on capacitor 1 and plus minus Q2 on capacitor 2 may differ. Now, the thing is same. Potential difference is same across both the capacitor, but charges plus Q1 minus Q1 and plus Q2 minus Q2 may differ on both the capacitor, following which equation Q1 is equal to C1V. So Q1 will dependent on C1. Potential is same across both the capacitors. So V potential is same for both the capacitor, but why charge will differ? Because of their different capacitance. Okay, so the capacitor with greater capacitance will get greater charge. So capacitor with greater charge, greater capacitance will store greater charge. So capacitor with lower capacitance will store lower charges because they are directly proportional. Okay. So capacitors in parallel, again same diagram. Figure 2.28, parallel combination of two capacitors and n capacitors. For the equivalent capacitor, the total charge Q equals Q1 plus Q2. Now, the total charge in the parallel combination is the charge on C1 capacitor and charge on C2 capacitor. Or if there are n number of capacitors, then charge on C1 plus C2 plus C3 and so on up to Cn. So, firstly, we will do for two capacitors. So, for the equivalent capacitance, the total charge Q on both the capacitor is Q1 plus Q2 with potential difference V on both the capacitors. So Q1 is equal to C1V and Q2 equal to C2V. Put this in this equation. So equivalent capacitor is 1 with charge Q equal to Q1 plus Q2. So and potential difference V. So Q is equal to, what is Q here? C into V. V is the potential difference across the combination of capacitors and C is the equivalent capacitance here. So this Q is equivalent to CV. C is equivalent capacitance as V is potential difference across the combination of capacitors. So equal to Q1 plus Q2. Q1 is C1V and Q2 is C2V. Okay. So after rearranging and solving, effective capacitance C is, so V will cancel out from all the parts of the equation and C becomes C1 plus C2. So in parallel combination, effective capacitance or equivalent capacitance will be C1 plus C2. So again figure parallel combination of A2 capacitors and N capacitors. General formula for effective capacitance C for parallel combination of N capacitors. Now for N capacitors, following similarly, Q equal to Q1 plus Q2 so on up to Qn, and Q is equal to CV. C is the equivalent capacitance and V is the potential difference across all the capacitors. So Q1 is C1V, Q2 is C2V and Qn is CNV, which gives C equal to C1 plus C2 so on up to Cn. So this is the equivalent capacitance for parallel combination of capacitors. Okay, next example. A network of 4 10 microfarad capacitors is connected to a 500 volt supply as shown in the figure. Determine A, the equivalent capacitance of the network, and B, the charge on each capacitor. Note that the charge on a capacitor is the charge on plate with higher potential. So that we have already mentioned that what we took charge on the capacitor is the charge on the higher potential. We know that net charge on the capacitor is 0, but we don't say in the numericals that charge on the capacitor is 0. We will take the charge on the positive potential or plate with higher potential. We will take the charge of that plate and we can say that charge on the capacitor is Q plus Q, that is on the higher potential, plate with higher potential. So equal and opposite to the charge on the plate with lower potential. So charge on capacitor is on the charge on the plate with higher potential, equal and opposite to the charge on the plate with lower potential. Okay, so what we have to find, firstly the equivalent capacitance of the network and the charge on each capacitor. So this is the diagram. So three capacitors C1, C2, C3 are connected in this form with C4 capacitor, and this is the 500 volt potential difference that is applied across these capacitors. So now we can see this C1 capacitor, plate of this C1 capacitor is connected directly to plate of this C2 capacitor. So they both are in series, and plate of C2 capacitor is connected directly to C3 without any internal connection, extra internal connection. So these three capacitors are in series. this fourth capacitor. So now plate of this C1 capacitor is connected to C4, but there is internal connection given from here, this point, and also from this point. So this capacitor is not in series with these three. Okay, so this capacitor will be in parallel to combination of these three capacitors. Okay, and combination of these three capacitors will be in parallel because the combination will have connection at common point with this C4. Okay, so how we will modify this diagram? Now again diagram. In the given network, C1, C2, C3 are connected in series. The effective capacitance C dash of these three capacitors is given by. So these three capacitors are in series. So their equivalent capacitance is 1 by C dash, which is equivalent capacitance of the series, equal to 1 by C1 plus 1 by C2 plus 1 by C3. Since all the capacitors are of same capacitance, that is 10 microfarad. So C1, C2, C3 all are equal to 10 microfarad. So C dash will be, after solving, 10 by 3 microfarad. Okay, so equivalent capacitance for the series combination of these three capacitors will be equal to 10 by 3 microfarad. Network has C dash and C4 connected in parallel. Thus the equivalent capacitance C of the network is. Now C dash, the combination of these three series capacitors in series, and C4, they both are in parallel combination. Okay, so does equivalent capacitance C of the network. Now for parallel combination we will simply plus add the both the capacitance. So C equivalent equivalent capacitance of these three capacitors in series plus the C4 which is in parallel. So C equal to C dash plus C4, which is 10 by 3 plus 10, which is equal to 13.3 microfarad. So the equivalent capacitance of this whole circuit is 13.3 microfarad. Okay. Now B part, we have to find the charge on all the capacitors. Clearly from the figure, the charge on each capacitor C1, C2 and C3 is the same. Okay, so since C1, C2 and C3 are in series, so charge on these three capacitors will be same. So let it be Q, and let the charge on the C4 is Q dash. Okay, so charge on C1, C2, C3, because they are in series. So suppose the charge on all these three capacitors is Q, and charge on C4 will be Q dash. So this is the diagram again. Now since the potential difference across AB is Q by C1, so potential difference across this C1, is Q by C1. On this, across this capacitor is Q by C2. Across BC is Q by C2. Across CD is Q by C3. Across CD means across the plates of this capacitor. Simply you can say across this C3 capacitor. Potential difference is Q by C3. So we have Q by C1 plus Q by C2 plus Q by C3 equal to 500 volt. So since you have to understand that the potential difference is same across this C4 and the combination of these three. Okay, so combination of these, since the potential is 500 volt, so potential 500 volt is across this C4 capacitor. So this C4 has potential difference across it 500 volt, and the combination of these three capacitor will have potential difference across them is 500 volt. But individually they have different potential difference V1, V2, V3. But collectively as a combination they have potential difference 500 volt across them. So potential difference across this Q by C1 is V1. This Q by C2 is V2. This Q by C3 is V3. So Q by C1 plus Q by C2 plus Q by C3 is equal to V1 plus V2 plus V3, which is equal to potential difference, total potential difference, 500 volt. Understood? Now, because potential difference across this C4 alone is 500, because it is parallel, in parallel combination. So Q dash is the charge on C4 upon C4 equal to 500 volt. Okay, this is the potential difference across. Potential difference is equal to Q by C. So potential difference across this V4 is equal to Q dash by C4 equal to 500 volt. Okay, so these are the two equations we have made. Now this gives for the given value of capacitance, which is okay. So now if we take this Q as common from this Q by C1 plus Q by C2 plus Q by C3, if we take Q common, it will become 1 by C1 plus 1 by C2 plus 1 by C3, which is equal to the 1 by C dash, and C dash is the equivalent capacitance of series combination. So this is the formula for that, 1 by C1 plus 1 by C2 plus 1 by C3. So it will become 10 by 3 microfarad. Okay, and the other thing, 500 volt. So charge will be Q, we have taken common. So this equivalent capacitance will go there in right hand side. So it will multiply with 500 volt. So charge on these three capacitors will become 1.7 into 10 to the power minus 3 coulomb. And Q dash will become 500 volt into C4. So C4 here is 10 microfarad equal to 5 into 10 to the power minus 3 coulomb. So charge on all the capacitors is known now. Okay. Consider a process. So now the topic is energy stored in the capacitor. Consider a process where charge is transferred from an initially uncharged conductor 2 to conductor 1 gradually until conductor 1 has charge Q and conductor 2 has charge minus Q. So this is the diagram. Okay. So this is a capacitor with plus Q charge. Capacitor is being charged. Okay. So we have to find the energy stored in the capacitor in static condition. When charges on both the capacitor will become maximum. Okay. So from from uncharged capacitor to fully charged capacitor, we have to find the energy, total energy stored. Okay. So initially capacitor is uncharged. Now we have connected the positive, this plate with positive terminal and this plate with negative terminal, so that the charges, because this plate is connected with negative terminal, so electrons on this plate will get repulsion. So charge electron will move from this plate to this plate. So charge will transfer from this plate to this plate. Okay. So this is equivalent to the induction of charge by this plate to this plate, because this plate will get negative charge due to negative terminal of battery, and this will get positive charge due to positive terminal of battery. Okay. So there is, we know that the only charge carriers are electrons. Positive charge doesn't move. So negative charge will move from this plate to this plate. Okay. So negative charge will move from this plate to this plate. Okay. So here negative charges appear, here positive charges appear. Okay. So it will at any instant, this plus Q dash charge, there is a Q dash charge on this plate and there is a minus Q dash charge on this plate. Okay. So to transfer delta Q dash charge from this plate to this plate, what work we have to done? Okay. So work done in a small step of building charge on conductor 1 from Q dash to Q dash plus delta Q dash. B. Total work done in charging the capacitor may be viewed as stored in the energy of electric field between the plates. Okay. So total work in charging. So this is the small work done to transfer charge delta Q dash from this plate to this plate. But to calculate the total amount of work done, we have to integrate the small work, or total work done in charging the capacitor may be viewed as stored in the energy of electric field between the plates. So when they are fully charged, there is electric field that exists between these plates, okay, in this way as shown in the diagram B. Okay, so this energy is stored in the form of between the plates in the energy of electric field. So to move a charge, positive charge from this point to this point, we have to do some work against the electric field. So this is the this work done is stored in the form of potential energy between the plates of the capacitor. Work is done externally in transferring a positive charge since conductor 1 maintains a higher potential than conductor 2. So work we have to do the external work in transferring a positive charge since conductor 1 maintains a higher potential than conductor 2. Okay, so conductor 1 is at positive potential, so it is at higher potential than conductor 2. So we have to do the work externally to transfer a positive charge from here to here. Okay, so for a small charge transfer delta q dash, when conductors have charges q dash and minus q dash, for any instant when capacitor is not fully charged but having charge q dash on its positive plate and minus q dash at its negative plate, the potential difference v dash at that instant is q dash by c, where c is the capacitance. So the total work done in this small step is, so for transferring delta q dash, a small charge, when there is a q dash charge on the positive plate of the capacitor and minus q dash charge on the negative plate of the capacitor. So what small work we have to done in this small step? That work done is v dash delta q dash, which is equal to q dash upon c into, what is v dash here? Q dash upon c, and into delta q dash. So integrating over the entire charging process. So to find the total work, we have to integrate over the entire charging process. That is from charging it to 0 to q charge. Okay, so integrate it. So this c will comes out as it is constant. So this integration q square by 2 and limits from q0 to q. Okay, so after putting limits, the work done is equal to q square upon 2c. This can be expressed as q square upon 2c. Okay, and you can also change this equation according to the situation. Okay, so you can eliminate from here q. So you can put q as cv. So here it will become q equal to cv, so it will become c square v square, and this is c. One c will cancel out, so it will become cv square by 2. So it is the second equation. Okay, now we will eliminate this c. C is equal to q by v. So put here q by v. One v will cancel out with this, so half qv. Okay, so you can shift between these three forms according to the question requirement. Work done by external force is stored as potential energy. So work done, what we are doing externally is stored as potential energy in the system, independent of charging process. It is independent of charging process, that how we are charging. It is not dependent on that. It is only depending on the final charge on the capacitor or the initial and final positions. The initial charge, final charge. Okay, so it is not dependent upon the charging process. For a parallel plate capacitor with area A and separation D, the stored energy can be represented as this: half q square by c. Okay, so q we can put it as A sigma. Sigma is the surface charge density into area, which will become q. Okay, so A square sigma square 2. So what is c for a capacitor? For a parallel plate capacitor with no dielectric medium between its plates. So C equal to epsilon naught A upon D. The surface charge density sigma relates to electric energy E as E equal to sigma by epsilon naught. So after solving this equation, A square sigma square, one A will cancel out. So it will become sigma square. and after multiplying by epsilon naught on above and on below, it will become epsilon naught square, and above it will become epsilon. So sigma square upon epsilon naught will become electric field square. Okay. Therefore, energy stored becomes half epsilon naught. After solving this equation, it will become half epsilon naught E square into AD. What is AD? Is the volume between the plates of the capacitor. Area into separation, which is volume between the capacitor plates. And this is the half epsilon naught E square. So AD represent the volume between the plates. The energy density of electric field is does. Okay, what is energy density? Energy upon volume. So this is the potential energy stored. So potential energy upon unit volume, potential energy upon the volume of the capacitor plate between the capacitor plates is equal to energy density. Okay, so we will divide the energy with volume and we will get half epsilon naught E square, which is energy density. Okay, the expression for energy density holds true for electric fields from any charge configuration. So it holds true for any charge configuration, linear charge configuration, sheet, it is aerial charge, or it is volumetric charge. So another example, 2.10, a 900 picofarad. Picofarad means 10 to the power minus 12 farad. Capacitor is charged by 100 volt battery, which is in the figure A. How much electrostatic energy is stored by the capacitor? So initially we have to calculate the energy stored. In the next part, the capacitor is disconnected from battery and connected to another 900 picofarad capacitor. What is the electrostatic energy stored by the system? Okay, these are the two scenarios. First scenario is this capacitor is connected with a 100 volt battery and charged. Now when it is fully charged, B part, it is connected with another capacitor of same capacitance. Okay, say both the capacitors have 900 picofarad capacitance. Okay, so now consider these both capacitors, and the second capacitor is initially uncharged. Only this capacitor is charged. So there is a transfer of charges from one capacitor to another capacitor until the equilibrium is attained. Then we will find the total energy stored on both the capacitors. Okay. The charge on capacitor is, again same diagram. Okay, initially in the first case, charge on the capacitor is Q equal to C into V, which is equal to 900 into 10 to the power minus 12 farad. Okay, into 100 equal to 9 into 10 to the power minus 8 coulomb. This is the charge on the total charge stored on the capacitor in the first case when it is connected with 100 volt battery. The energy stored by the capacitor is half CV square, which is equal to half QV. You can find directly also by applying half CV square. Okay, but you can also find charge prior to this if it is asked, particularly in the question. If it is not asked, then you can find directly with half CV square also. Okay, so here it is half CV square equal to half QV. So we have found the charge 9 to 10 to the power minus 8 coulomb into V is 100 volt. So it will become energy stored is, after solving, 4.5 into 10 to the power minus 6 joule. This is in the first case A, when this capacitor is connected to 100 volt battery. So the energy stored in this capacitor is this 4.5 into 10 to the power minus 6 joule. Now B part, in steady situation, the two capacitors have their positive plates at the same potential and their negative plates at same potential. So they are connected in parallel. Positive plate of first capacitor is connected to another capacitor that is uncharged. Another capacitor is uncharged initially. We have charged only one capacitor, not other. So they are connected in parallel like this in the second diagram. Okay. So let the common potential be V dash. So now the charge will start flowing from this capacitor to this until the static condition is attained. Okay. So the common potential that is after connecting these both the charges will be V dash. The charge on each capacitor will be Q dash equal to CV dash. Okay. Now charge will change on the both the capacitor because there is a distribution of charge among both the capacitors. So by charge conservation, charge Q will remain conserved. Okay. So initially this is charged with Q charge and this is uncharged. So since both the capacitors are of same capacitance, okay, so this charge will transfer to this capacitor. So since they are identical, so charge distributed on both the capacitor will be same. So charge on first capacitor will be Q by 2 and charge on second capacitor will also be Q by 2. And sum of both the charges will become the equal to the initial charge on the first capacitor. Okay. So by charge conservation, Q dash is equal to Q by 2. This implies after putting this Q dash equal to Q by 2 in this, V dash will be V by 2. The common potential of these two capacitors is V by 2. And charges are distributed equally on these capacitors because they are identical. The total energy of the system is total energy of the system of two capacitors is 2 into half Q dash V dash. Half Q dash V dash is the energy of one capacitor and multiply by 2 is the energy of both the capacitors. After putting Q dash and V dash, we will get 2.25 into 10 to the power minus 6 joule, which is half as compared to the energy in the previous case. Thus in going from A to B, from A condition to B condition, though no charge is lost, the final energy only half of the initial energy. Why? Why final energy of both the capacitors is half of the initial energy? Where has the remaining energy gone? Half energy, where has half energy gone? So here is the answer. There is a transient period before the system settles to the situation. So when we connect the charged capacitor with uncharged capacitor, there is a transference of charges due to which current begins to flow from one capacitor to another until the static condition is being achieved. Until the charge on both the capacitor is distributed equally if they are identical. During this period, a transient current flows from the first capacitor to the second. Energy is lost during this time in the form of heat and electromagnetic radiation. When charged capacitor is connected with another identical capacitor of same capacitance, charges begins to flow and hence current is induced. This transient current flows from first capacitor to second. Therefore, due to flow of the current, energy is lost in the form of heat and electromagnetic radiations. That's why half of the energy is lost and we only got final energy half of the initial energy. Okay. So thank you. I hope you enjoyed the session.